Right, so this is a compound called histrionicotoxin. Very difficult to see actually, it's just a tiny speck in there, probably less than a milligram of this compound in this vial, and yet that'll be enough easily to kill a human being. So it's an incredibly toxic part of the nature's chemical warfare. Frogs have evolved all sorts of mechanisms to defend against predators and birds and what have you. So this is one of the compounds they can excrete when they're under attack. So on the surface of the frog you get this gooey excretion if it's under attack. It looks like a white foamy substance. And these are only frogs which are usually found in Latin America, things like that. They're endangered species, so we're not allowed one, but here's my model of one. But actually they're even smaller than this. So the frogs you get over in this country are fairly sizable. These frogs are probably about the size of your thumbnail. Very, very tiny, very brightly coloured. So this one's blue, but this is nowhere near as bright as some of these frogs. There's reds and yellows. It's essentially screaming danger. So when the bird comes in, it maybe peck it, the frog needs something to act really quickly. And over the millions of years, they've developed these compounds and they actually act on the nervous system. So what they do is they paralyse the bird instantly. So the bird is 1 minute about to have dinner, the next minute is completely frozen like a statue. And of course the frog can hop away. The bird eventually dies of asphyxiation because the lungs, all the breathing, all those muscles, everything gets paralysed. We'll go back to this again. So it's probably just less than 1 milligram in here, and you can't see it. It's so small. It's about a speck of dust sort of size. About 3 milligrams were first isolated from 1,100 frogs. So you can see that these compounds are so potent that the frogs really don't need to make very much of this in order to be effective in their defence against multiple predators. When the Spanish and others, the French went out to South America hundreds of years ago now when they were exploring, of course they turned up and they thought, well, the native people here just have bows and arrows or spears. These guys will be a walkover, but of course they weren't, because what they had were poison darts. So sometimes these frogs are called poison dart frogs or poison arrow frogs. So what they would do, they would capture these frogs, and these frogs only make this toxin when they're in the natural environment. If you have them in captivity, they don't have the right dietary source, they can't make these molecules. So these native Indians would go and they would keep them in a hollow tube, and when they needed them, they would take a spear or a dart and they would put it down the mouth of the frog to the other end, to its leg, and oddly enough that would make the frog sweat quite a bit. And you'd get all this white, gooey excretion coming from the skin, and you just take your arrows and you just twirl it around in this secretion. And these arrows then would be poisonous for around about a year. So these compounds are quite stable entities, quite stable compounds. And of course what happened was the invaders came over, and of course when they got shot with these darts or spears with this poison on the tip, they would be paralysed just like the bird, just like anything else. So birds are quite small, humans are quite big. Still sub-milligram quantities of this material is enough to paralyse and indeed kill a human being. So these are very potent compounds. Right, well you can get it from frogs, but if you remember I said 1,100 frogs will give you about 3 milligrams of this material. We wanted to make these compounds in a synthetically viable way, so you could make grams if you needed to allow these further studies to go on. These could also be potentially useful compounds for the treatment of pain, maybe in the future. Certainly good lead compounds for study, because pain messages also go through the nervous system. So this is this particular one molecule here. So this is perhydrohistrionicotoxin. And it's actually, this is a synthetic compound. So there's about 15 of these compounds, and it's just these two side chains which are different. This core structure in the middle is always the same. The blue one here, that's nitrogen. This is an oxygen, so this is a hydroxyl function here. And it's the combination of these two and the exact spacing between these two which is key to why this molecule works. So this mimics a natural neurotransmitter used to convey the message between two parts of the nervous system. So you can think of a nervous system as an electrical cable, and then you'll get a connector junction. So imagine two connectors coming together, a plug and a socket. Now the acetylcholine molecule transmits from the plug to the socket. The spacing of these two functionalities here is absolutely key. So these fit the key that acetylcholine normally would fit in to trigger the response. If you were clumsy, or indeed if you got shot by a poison arrow, this gets into your bloodstream. It can get immediately to the peripheral nervous system, so that's all your muscles, your heart, your lungs, anything that moves in your body, and it can block the receptors in those, or block the signals from your brain to your lungs, for example, to tell it to breathe in and out. Now, you don't consciously think that you're doing that, but your brain's a very clever thing. It sets so many things on autopilot. But it's constantly sending out messages, many, many hundreds a second, to control what's going on in your body. And this little molecule here, and it would take just a few of these molecules to completely shut down those muscular neurotransmissions, if you like. If it got into your central nervous system, that is in your spine and your brain, it could completely wipe out any messages that are coming from your hands, from any senses to your brain. So in many ways that's why it could be very useful for pain management.